Hi class, in this video we're going to prove the power rule. Now here's the basic idea. If you have a function that you have a variable and raised to an exponent, as you take the derivative, you simply drop the actual exponent and reduce it by 1. So the proof's going to start by defining the function, and I have it here as technically n is any real number, and then also the important part is that you're able to define the exponents x to the n and n to the, or x to the n minus 1. Now, as we apply the definition, this one becomes really messy because of the following. You technically have that this is the limit as h goes to 0, but then as you do the substitution of x plus h, we're going to have x plus h to the n minus technically the values of x to the n. And all of this is over h. The part that becomes messy is that x plus h to the n actually has a binomial expansion, which happens to be this whole mess. Now, for simplicity, keep in mind that you're going to have these, the a is your x's, your b is your h's, and all the terms starting on the second one, it's actually going to have an h all the way into the infinity. And then for simplicity, I'm just going to use the first 3 terms that pop out of the formula, and then just rewrite it with the plus dot dot dot. And then also don't forget about the x to the n, which represents the subtraction of f of x. So as we're substituting the actual x to the n, we're going to have that this is equivalent to the actual limit as h goes to 0 of, and the first term is just going to be x to the n. So this is x to the n plus the values of n, x to the n minus 1 times b, but b happens to be an h here. And then plus, and I'm just going to get the first 3 terms. So you're going to have a n times n minus 1 divided by the 2 factorial times, and we have an x to the n minus 2 and h to the second plus, and technically the pattern continues. Every term's h is going to be increasing. You have h to the second, h to the third, all the way to the last one, which happens to be a x to the n, or I mean a h to the n. And then we still have the minus, so minus the x to the actual n. And then all over the values of h. Now, as soon as we do the substitution with the actual binomial expansion, we're going to actually see a cancellation. So the first term, x to the n, and x to the n cancels. And let me rewrite it without those terms. So in this case, we end up with the actual limit as h approaches 0 of the first term happens to be an n, x to the n minus 1 times h, plus technically n times n minus 1 divided by 2 factorial times x to the n minus 2 times h squared plus, and then you have the h to the n. The last term cancel all over the values of h. Now, in the next step, what we're going to do here is technically divide each of the terms, and keep in mind that we have an infinite amount of terms by the values of h, and this is going to cancel at least one of the terms from the numerator. So as we carry this division, we're going to be rewriting it as this is equivalent to the actual limit as h goes to 0 of, and as you divide by the first term, h cancels. So we're left with n, x to the n minus 1 plus, and then we have n minus 1 over 2 factorial times x to the n minus 2 times h. This h cancels one of these. Keep in mind that this is in fact an entire term. So as you carry the division, h goes away, you cancel one of the h's, so this is to the first power. In this pattern, it's going to actually continue all the way until the last one. So the last one, so you're going to have plus, plus, and this will be h to the n minus 1. I'm just rewriting h to the n over h to the first, which is equal to h to the n times h to the negative 1, and then combining them, which is going to give us the h to the n minus 1. Now, the next portion, we're actually defining, or in this case, evaluating the limit of each of the terms, and technically all the way to the infinity. On the good news, the first term is the only one that doesn't cancel. So we're left with technically equivalent to the limit as h approaches 0 of the values of n and x to the n minus 1, which happens to be a constant, plus the actual limit as h approaches 0 of n minus 1 over 2 factorial times x to the n minus 2 times h. Keep in mind that this one will have an evaluation of h. So every term, we're going to be evaluating h. And then technically plus, and then the last one is going to have the actual limit as h approaches 0 of h to the n minus 1. And then what we're going to see is that as we're evaluating the limit, so for the first term, it does not have any h's. This is an actual n. And let me fix it because it looks like this is an actual n. And it represents a constant, no h. So technically this is just n. X to the n minus 1 plus. And technically as you're plugging in the 0, it's going to cancel this term. So you do have n times n minus 1 divided by 2 factorial times x to the n minus 2 times 0, and every term is going to go to 0. And that's going to be technically 0 raised to the n minus 1. Keep in mind that there is going to be an exponent, and we have defined, so technically, that any value to the n, or any value here, is actually defined, and we're able to evaluate. So all of these, starting with the exception of the first one, are actually going to go to 0. And then we're technically left with just the value of n, x to the n minus 1, plus 0, which is equal to n, x to the n minus 1. At this point, this is actually the end of the proof. Let me just rewrite the original problem. And in this case, let me just rewrite it as f prime of x is equal to n x to the n minus 1, where f of x is equal to x to the n. And that is technically the end of the proof. It was a little bit messy, especially as we're actually plugging in the binomial expansion into the formula. You technically only need the first 3 values, and then the pattern will actually continue. But here you can see that as soon as you plug in this quantity, it makes a mess in terms, and then the pattern continues. So that means that every value in between cancels out as well once you're taking the limit. And keep in mind that this is technically considered one whole term. So every one of the terms, it's going to cancel out, leaving us only the n and the x to the n minus 1. which technically happens to be the formula. That's actually it for this one.